In this video, we're going to discuss exponential functions and what their graphs look like. So an exponential function is a function that looks like this. This is different than any other function we've dealt with because now the variable is in the exponent. So we've seen things where x is the base and we have a number as the exponent. Now it's reversed. So the base is a number and the variable is in the exponent. And the base can be any positive real number except for 1, because 1 to any exponent will always give us 1, so that would not be an exponential function. But the base can be any positive number except 1. So we're going to start here by just graphing some exponential functions by plotting points and kind of noticing some patterns depending on what the base of the function is. So we're going to start here with a base of 2. So we're going to graph the function y equals 2 to the x. And just like any time we're looking at a new function and trying to figure out what the graph looks like, it's a good idea to use a couple negative x values, a couple positive x values, and 0, as long as your function allows for that. So we'll do that here. And so I'm going to start actually with the largest one and work backwards. So if we plug in 2 for x, we've got 2 squared, which is 4. If we plug in 1 for x, we have 2 to the first, which is 2. If we plug in 0 for x, we have 2 to the 0, which is equal to 1. And then 2 to the negative 1. A negative 1 exponent means we're taking the reciprocal of the base. So 2 to the negative 1 is just the reciprocal of 2, which is a half. And then for any other negative exponent, the negative part means we're taking the reciprocal of the base and then we raise it to the positive exponent. So since it's a negative exponent, our base becomes 1/2. We're raising 1/2 to a power of 2. So 1/2 squared. Which is 1 squared over 2 squared, so that's 1/4. So if we plot those points on our graph, we can kind of start to see what this graph is going to look like. So we're getting this curve here, and we can see that as we move to the right, it's increasing pretty quickly. Exponential functions, that's one of their main characteristics. Exponential functions increase really quickly. You may have heard someone, even just in conversation, say that something was growing exponentially. It means it was growing really fast. And you can kind of see that if you keep taking higher exponents of 2, you're going to get, 9, 16, not 9, 8, 8, 16, etc. So it's increasing really fast to the right. And then as we go to the left, let's think about what's going to happen. So we were getting smaller y values as we took smaller x values. But raising 2 to a negative exponent is always going to give us a positive number because we're taking 1/2 to a positive exponent essentially. So we're never going to get 0. You can't raise 2 to a power and get 0, and you can't raise 2 to a power and get something negative either. So what happens as we move to the left is the graph is going to get really, really close to the x-axis, but it's never going to touch or cross it. And so the x-axis is a horizontal asymptote for this graph. So the line y equals 0, which is the x-axis, is a horizontal asymptote for this function. And like we said, as it goes to the right, it's just going to increase really quickly. Now let's see what happens if we use a different base other than 2. So let's graph 4 to the x. So we'll use the same x values, that way we can kind of compare what's going on here. So if we substitute 2 for x here, we have 4 squared, which is 16. 4 to the first is 4. 4 to the 0 is 1. Then we have 4 to the negative 1, which again means we're taking the reciprocal of 4, so that's 1/4. And then 4 to the negative 2 means we're going to take the reciprocal of the base and then square it. So that's 1 squared over 4 squared, so 1/16. So both graphs have this point 0, 1 because any base raised to the 0 is going to be 1. So that's a point that we're going to see on all of our exponential functions where it's just a number to the x. Then we have the point 1, 4. And then we have the point 2, 16, which is going to be off my page here. But you can see that this graph is going to be above the other one in quadrant 1 because the base is larger and we're getting larger y values for the same x value. If we go the other direction though, we have the point -1, 1/4. That's going to be below the point we had on the other graph, which was -1, 1/2, because 1/4 is less than 1/2. And then 1/16 is going to be less than 1/4. So we get a similar shape as we go to the left. Again, we're not going to get any y values that are negative. We're not going to get a y value of 0. They're just going to get really close to 0. You can see they're getting smaller there, just like they were for the other function. So this one is also going to have a horizontal asymptote of y equals 0. And it's also going to increase quickly as we move to the right. It's going to be increasing even more quickly than the first one. Let's see what happens when we have a base that is less than 1, because it's going to look a little bit different. So let's say we want to graph 1/2 to the x. Because we said our base can be any real number as long as it's not 1, because then we just get all 1 for all the y values. So we're going to use the same x values here that we did before. And if we substitute 2 for x, we're going to have 1/2 squared, so that's 1 squared over 2 squared, so 1/4. And then 1/2 to the first is 1. 1/2 to the 0 is going to be 1. 1/2 to the -1. That -1 exponent does the same thing it did before. It means take the reciprocal of the base. So the reciprocal of 1/2 is 2. And then similarly, any other negative exponent means take the reciprocal of the base and then raise it to the positive exponent. So we have 2 squared there, which is 4. If you compare this table with the table we had for 2 to the x, the y values are the same, they're just going in the opposite order. We've basically had a horizontal reflection. We had a 0.24 before, and now it has been reflected over to negative 24. We had a point at 1, 2, now it's at negative 1, 2, and we'll talk more about why that is in a little bit. But it's basically going to be the same shape then, just reflected horizontally over the y-axis. And so as we move to the right now, it's going to approach that horizontal asymptote of y equals 0. We're still going to get close to 0, but not ever reach 0. We still have that point 0, 1 that we had on our other graphs as well. And so if we look at 1/4 to the x, it's going to be kind of similar. 1/4 squared is 1/16. 1/4 to the first is 1/4. 1/4 to the 0 is 1. 1/4 to the negative 1 is going to be the reciprocal of 1/4. And then 1/4 to the negative 2 is going to be 4 squared. So again, this is basically a horizontal reflection of 4 to the x. We used to have 1, 4, now we have negative 1, 4. We had negative 1, 1/4, now we have 1, 1/4. Still have that point 0, 1 because that's on the axis we're reflecting over. And we're still going to approach that horizontal asymptote y equals 0 as we move to the right. So let's just kind of summarize then. What is the graph going to look like in general? And we saw it's different for a base greater than 1 versus a base that's less than 1. So, and the base really is going to be between 0 and 1 here because we already established on the first slide with our definition that the base is not going to be negative. So what we saw then was we saw some common things on the graph when we graphed 2 to the x and 4 to the x, right? Those were our bases that were greater than 1. They both had this point 0, 1 in common. They both had the same horizontal asymptote. They both increased quickly as we moved to the right. And so that's going to be the case for any graph of b to the x where b is greater than 1. You're going to have that y-intercept at 0, 1. You're going to have a horizontal asymptote of y equals 0. It's going to be increasing from left to right. Let's talk about the domain and range. So the domain for a basic exponential function like this is going to be all real numbers because we can substitute any number for x and we will get a real number for our output. We saw we can use negatives, positives, 0, everything works. And the graph goes forever left and right. The range, though, is not all real numbers. We saw we never had any negative y values, and we never had a y value of 0. We just got closer and closer to 0 without ever reaching it. So our range is all numbers greater than 0, because we do increase upward forever. So since it's just numbers strictly greater than 0, we have parentheses there, because we can't have a y value that's equal to 0. Okay, then we saw with our graphs of 1/2 to the x and 1/4 to the x that the graph will be decreasing from left to right once we have that base less than 1. But a lot of other things were the same. We still had the y-intercept at 0, 1. We still had a horizontal asymptote, y equals 0. The domain's still all real numbers. We still were able to plug any number in for x that we like. The graph goes forever left and right. And the range is the same as well. We had only positive y values for these as well. So really similar information for both types of bases. Same domain, same range, same y-intercept, same asymptote. It's just the base less than 1 is going to cause the function to decrease. Let's talk briefly here about transformations of these graphs. It's going to work the same way it does for all the other functions we've done. So multiplying by -1 is going to do a reflection, just like in the past. You'll see the negative out front if it's a vertical reflection. And you do want to be careful there because that's basically like multiplying by -1. And we multiply after we raise something to an exponent. So that's our order of operations. So you would do b to the power first and then multiply by -1 if you're plugging in an x value. The horizontal reflection is going to be when it's a negative x instead of a positive x. And we've kind of seen that a little bit already because b to the negative x is just 1 over b to the x, because a negative exponent means we take the reciprocal. So for example, we saw that 2 to the negative x is the same as 1/2 to the x. So when we graphed 1/2 to the x, that's why it was a reflection of 2 to the x, because it was essentially 2 to the negative x. So multiplying by -1 still does a reflection, and then adding or subtracting is still going to do a shift. A lot of books will put the addition out front for a vertical shift, but these are equivalent. And then anything that's changing where x is going to be a horizontal change. That's the same as it's been for other functions. If the change happens where x is, it's horizontal. If it doesn't, then it's vertical. So for example here, this is a transformation of 2 to the x because we have that base of 2. So that's our basic 2 to the x that we graphed a few minutes ago. And we see some addition or subtraction, so that's going to be shifting. The x plus 1 in the exponent, since that's where x is, that's going to be your horizontal shift. So that's going to shift it to the left 1. And then subtracting 2 is not happening with x, it's outside the original function. So that's going to be a vertical shift. That's going to be a shift down 2. And so you can do this visually if you want. I think especially for horizontal shifting, that's usually a good way to go. So if I was at -1 with this point before, and now I'm going to come to the left 1 and I'm going to be at -2. The point at 0 is going to move over to -1, and the point at 1 is going to move over to 0. And then to shift up or down, we're just subtracting from the y value. So we're going to have -1.5 here, -1, and 0. So just the old y value minus 2. So let's graph this. -2, 1.5, -1, -1, 0, 0. So once we do transformations, it's possible that that basic information we just discussed might change. For example, our y-intercept has changed, right? Because we moved down. The horizontal asymptote is going to change as well because the x-axis is definitely not an asymptote anymore if we're crossing it and going below it. So what happens is, since this whole shape is shifting down, that horizontal asymptote is going to come down with it. So the horizontal asymptote also moves down too. So instead of it being the line y equals 0, it's going to be the line y equals -2. The shape stays the same because all of the points have just been moved left and down. If we look at the domain and range here, the graph still goes forever to the left and right. We can still substitute any number for x and get a real number output. So the domain's always going to be all reals for these. But if you do something vertically, the range might change. And it definitely changed here, right? The range used to be numbers greater than 0. Now the range is numbers greater than -2, because that's where our horizontal asymptote is. So for example, if we want to graph y equals -2 to the x, this is a reflection, and it's a vertical reflection because it's not with x. The exponent is still just x, so nothing's changing horizontally. But all the old y values are getting multiplied by -1. So this is a vertical reflection. Multiply the old y values by -1. So since all the y values were positive, now they're all going to be negative because we took all those positive numbers and multiplied them by -1. And when you go to drawing the shape, it helps to know that this is a reflection. So if you can envision taking this curve and reflecting it down over the x-axis, it's still going to approach the x-axis as you go to the left, and then it's going to decrease really fast to the right. The y values still will never reach 0. We still have the same horizontal asymptote. We just reflected over the asymptote, so that's why it didn't change. But the range is going to change again because again we had a vertical change. So now instead of all positive y values, we have all negative y values. So that affects the range. The domain's still going to be all reals like it has been for all the other ones.